Bismillahirrahmanirrahim. In this lecture, we will discuss the dimensions of physical quantities in detail. In this lecture, we will start from definition of dimensions. Then we will discuss the dimensions of base quantities, sets of dimensions in mechanics, electricity and magnetism, and thermodynamics. We divide physics in three major groups, and in each set, which set of dimensions is valid is used, we will talk about that. Then we will discuss the dimensions of derived quantities, dimensions of supplementary quantities, and after that we will discuss some features of dimensions, some characteristics or features of dimensions, and also the applications of dimensions. We can name it as applications or uses of dimensions. And then finally, we will talk about drawbacks of dimensions, or we can say that we will talk about the limitations of dimensions. So we start our lecture. As we know that in physics, we divide the physical quantities in three groups. Physics is based on physical quantities, so uh, we start from physical quantities. As we know that physical quantities are divided into three groups, that is base quantities, derived quantities, and supplementary quantities. For each physical quantity, a dimension is defined. So first of all, we define dimensions. Dimensions are defined as each base quantity denoted by a specific symbol and written within square brackets. Base quantities. The dimensions are defined with respect to base quantities. And as we know that other quantities such as derived quantities and supplementary quantities are the combination of base quantities. So with respect to base quantities, we define dimensions as each base quantity denoted by a specific symbol and written within square bracket is called a dimension. Each base quantity has dimension. So this is the definition of dimension. And dimensions basically tell us about the nature of physical quantity. Dimensions tell us about nature of a physical quantity. As we know that mass is a base quantity, length is a base quantity. So all of these quantities have different natures. Here is the set of dimensions of basic quantities. Dimensions of base quantities, basic, not basic, but the term is base quantities. So there are 7 base quantities named as length, mass, time, and furthermore. Length is a base quantity and its unit is meter, and its dimension is denoted by capital L, and this symbol is written within square bracket. Mass, its unit is kilogram and its dimension is denoted by capital M. Time is a base quantity and its dimension is denoted by capital T. Electric current is a base quantity. Its unit is ampere and its dimension is denoted by capital A with the symbol of its unit. Or we can also denote the dimension of electric current with capital I. But most of the time we use capital A for the dimension of electric current. Thermodynamic temperature, its SI unit is Kelvin and its dimension is also denoted by capital K, the symbol of its unit. Or we can also denote the dimension of thermodynamic temperature with angle theta. Intensity of light, its unit is candela and its dimension is denoted by symbol of its unit, that is CD. Or we can use the symbol of capital J. Amount of substance, its unit is mole and its dimension is denoted by the symbol of its unit, that is mole, or in some books it is written as capital M. So this is the set of dimensions. I shall use the dimension of electric current as capital A, temperature as capital K, and so on. So this is the set of base quantities dimensions that we are going to use in our further discussion. So the dimension is defined for each base quantity, as its statement denotes that dimension is denoted by a specific symbol and that is written within square bracket. So here is this the set of base quantity dimensions of base quantities. Now we shall talk about the set of dimensions that is used in mechanics, electricity and magnetism, and in thermodynamics. In mechanics, in mechanics, all physical quantities involve the base quantities as mass, length, and time. All derived quantities in mechanics are combination of these base quantities. So the dimension for mass is capital M, the dimension for length is capital L, and dimension for T is capital T. So this is the set of dimensions that is used in mechanics. And in electricity and magnetism, we deal with the terms involving mass, length, time, electric current, and intensity of light. Intensity of light means intensity of electromagnetic radiations. So in electricity and magnetism, with respect to these base quantities, the set of dimensions is the dimension of m, the dimension of length, dimension of time, the dimension of electric current, and dimension of intensity of light denoted by CD. So this is the set of dimensions that is used in electricity and magnetism. And in thermodynamics, in thermodynamics, we deal with physical quantities involving mass, length, time, and temperature, and similarly uh, the number of moles, amount of substance. So with respect to these base quantities, this is the set of dimensions that is used in thermodynamics. So this set consists of mass, length, dimensions of mass, length, time, temperature, and amount of substance. Now we will talk about the dimensions of derived quantities. As we know that the derived quantities are combinations of base quantities. So the dimensions of derived quantities are combinations of dimensions of base quantities. So as we know that speed is a derived quantity and it is defined as length over time. So dimension of speed is equal to the dimension of length divided by the dimension of time. When we enclose a physical quantity in square bracket, it means that we are talking about the dimension of that quantity. So it is termed as speed is equal to length over time, and we read it as the dimension of speed is equal to dimension of length divided by dimension of time. And symbol for speed is v. Dimension for length is denoted by capital L, and dimension for time is denoted by capital T. So this is the dimension of speed, and speed is a derived quantity. We can see from this expression that the dimension of this derived quantity is the combination of dimensions of base quantity, and a final answer is written within one square bracket. So we combine these two square brackets and this will become in one square bracket as the dimension of v is LT inverse. Okay, next we calculate the dimension of acceleration. As we know that acceleration is defined as a rate of change of velocity. So dimension of acceleration is combination of dimension of velocity and time. We have calculated the dimension of velocity as LT inverse. So it is LT inverse, and dimension of time is capital T. We combine these terms, we combine these two square brackets so that final answer is written within one square bracket. So dimension of acceleration will be A is equal to LT inverse, and this term when comes up it becomes T inverse. Its power is 1. And when the term in the denominator comes upwards in the numerator, then its power becomes, the sign of its power changes. So finally the dimension of acceleration is Lt minus 1, T minus 1, and it is equal to Lt minus 2. So this is the dimension of a derived quantity acceleration. And as we can see from this expression, that dimension of acceleration is the combination of dimension of length and time, which are base quantities. We can write another example, as we know that force is defined as ma by Newton's second law. So the dimension of force is written as dimension of mass into dimension of acceleration. It is equal to the dimension of mass m, capital M, and the dimension of acceleration is Lt minus 2. Finally, combining these two square brackets, we write our answer as mLt minus 2. So this is the dimensional formula of force, which is a derived quantity, and a dimension of this derived quantity is the combination of base quantities. And now we discuss the dimensions of supplementary quantities. There are two supplementary quantities named as plane angle and solid angle. The SI unit of plane angle is radian and it has no dimension. Similarly, the solid angle does not have any dimension. The SI unit of solid angle is steradian. These are only physical quantities which do not have any dimension. So we can say that plane angle and solid angle are dimensionless physical quantities. Now we see that why plane angle and solid angle do not have dimension. First of all, we talk about plane angle. Plane angle is the angle between two radii of a circle. Suppose we have a circle having radius r. We take a point P1 and another point P2 on the circumference of circle, and r is radius of this circle. From point P1 to point P2, the distance on the circumference of circle is called arc length of circle, and we denote it by L. So plane angle is defined as it is equal to arc length of circle divided by radius of circle. And as arc length is L and radius is R, and we denote plane angle by symbol theta. So for the dimension of plane angle theta, we have to write the dimension of length and R. As length and radius both are measured in meters, both represent the same physical quantity, that is length, which is measured in meters. So dimension of arc length is L and dimension of radius is also L. it becomes L, L inverse, and finally combining these two square brackets, we get L's power 1 minus 1, which is L in power 0, and any quantity having its power 0 is equal to 1. It means theta have no dimension, and we write it as theta is dimensionless. And we can write the dimensional formula of plane angle theta as theta is m in 0, L in 0, and T in 0. Means theta does not depend on mass, length, or time. Theta is a dimensionless quantity. So supplementary quantities, plane angle and solid angle, both do not have dimension, and here we have discussed why plane angle do not have dimension. Similarly, I shall discuss about the solid angle and about the dimension of solid angle. The solid angle, plane angle is two-dimensional angle, and solid angle is a three-dimensional angle. And solid angle is the angle subtended at the center of sphere. Suppose r is radius of sphere. If we take small area on the surface of this sphere, then angle subtended by this area at the center of this sphere, which is three-dimensional angle, that is called solid angle. If we take large area of surface of sphere, then the value of solid angle will be large, and if we take small area of sphere, then value of solid angle will be small. So solid angle is the ratio of area of surface of sphere divided by square of radius of sphere. For area we use symbol A, and for radius we use R, as it is square of radius, so R square. And for solid angle the symbol is omega. This is the definition of solid angle. Now we calculate the dimension of this solid angle. For dimension of solid angle, we enclose it in square bracket, and dimension of solid angle is the combination of dimension of area and dimension of r square. The dimension of area is L square, and radius has the dimension of L, as it is square of radius, so its dimension is L square. Combining these two brackets, we get this is L square minus 2, 2 minus 2, which is equal to L's power 0, and that is 1. It means solid angle is dimensionless. Or we can write the dimensional formula of solid angle in terms of mass, length, and time as m in power 0, L in power 0, and T with power 0. This is dimensional formula of solid angle in terms of mass, length, and time, and it is a dimensionless physical quantity. So plane angle and solid angle do not have dimensions. And remember that plane angle is a two-dimensional angle and solid angle is a three-dimensional angle. Now we discuss the characteristics of dimensions, or we can say that we discuss some features of dimensions. Some features of dimensions. First of all, we can note that the expressions of dimensions, are manipulated as algebraic expressions, as algebraic quantities. As in algebra, we can add, subtract, multiply, or divide the quantities. Similarly, in dimensions, we can add the dimensions of similar quantities. We can subtract, multiply, or divide the dimensions of physical quantities. And we solve these expressions as we solve expressions in algebra. For example, if we have the dimension of L plus the dimension of L, then we can write it as this uh, both these are the dimensions of same quantity, so it is equal to 2L. Similarly, we take the example as L square over L is equal to, my camera having problem with the focus and I am trying to fix it. Okay, what is the problem here? So this expression can be solved as we solve equations in algebra. So it comes out to be L. So in the dimensions, expressions of dimensions are treated as the quantities in algebra. Uh, my camera is having some problem with focus and I should fix it. The second feature of dimensions is that dimensions do not tell about the quantity of a physical quantity. and instead of this term quantity, it is better to use the term magnitude. Dimensions do not tell about the magnitude of a physical quantity. Sorry, this is one of the drawbacks of dimensions. So we are discussing the features of dimensions. So the second feature is that dimensions tell us about the qualitative nature of a physical quantity. Qualitative nature means dimensions tell us that which quantity, physical quantity we are dealing with. For example, I can write a term height, radius, light year, or uh, I can write about I can write the diameter of circle. These are different names: height, radius, light year, diameter. But basically, all of these names are representing length. Height is length, radius is length from center of circle to its circumference. Light year is the distance covered in 1 year by light. So this is also length. Diameter is also length. All these terms are calculated, measured in meters, which is the unit of length. It means by nature all these terms are same, that is they are representing the length, and all these terms have same dimension denoted by L. So dimensions tell us about physical quantity. If we are talking about mass, then we will write the dimension of mass, that is capital M. Whenever we see written capital L, capital M, or capital T written within square bracket, we can easily tell that that particular term is representing some physical quantity. And mass is a physical quantity different than length. Length and mass are two different quantities having different nature. So dimensions tell us just about the nature of a physical quantity. We can take here another example. For example, if we take the term velocity, we can talk about velocity in a number of ways, as simply velocity, instantaneous velocity, or someone may say that average velocity. All these terms have different sense, but by nature they are same. For example, velocity is defined as a rate of change of displacement. Instantaneous velocity has the formula as limiting value of delta t approaches to 0, delta d over delta t, and average velocity is also written as total displacement over total time. And displacement is representing length, so its dimension is capital L, and time has dimension of capital T. So the dimensional formula of velocity is LT inverse. Similarly, we can write the dimension of instantaneous velocity, which comes out to be LT inverse the dimension of average velocity comes out to be LT inverse. When we see the dimension, we can note that velocity, instantaneous velocity, average velocity, all these terms have same dimension. It means they have same nature. Or we can say that the dimension tells us that tells us about a quantity, about the nature of quantity. For example, average velocity is a quantity having length and time. So simple is that from these two examples you can see that dimensions or dimensional formula tells us just about the nature of a particular physical quantity. Maybe names are different, but the nature, if the nature is same, maybe the names are different, but if the nature of that quantity is same, then dimensions are denoted by the same formula. Okay. The third feature of dimensions is that dimensions of a particular quantity do not depend on the mathematical formula being used for that quantity. Dimensions of any particular physical quantity do not depend on the expression that is being used for that quantity. For example, we can take the example of area. Area of circle, and I talk about area of rectangle. The formula for area of circle is A is equal to pi r square, and mathematical form of formula for area of rectangle is length into width. Now we calculate dimension of area from these two different formulas. So I write again area of circle and area of rectangle. Formula for area of circle is pi r square, and for rectangle is A is equal to length into width. Dimension of area, dimension of pi into dimension of r square. Pi is a dimensionless number and r square has a dimension of l square. So dimension of area is l square. From this formula, the dimension of area comes the dimension of length into dimension of width. Length and width both are measured in meters. So length has dimension of L and width has dimension L. And finally, dimension of area comes out L square. We have used two different formulas. A is equal to pi r square and A is equal to length into width. But we see that the dimensional formula of area in both cases is same. It means that dimension of a particular physical quantity does not depend on the mathematical expression. any physical quantity have the same dimension whatever formula may be used for that quantity. So these are some features of dimensions. Now we talk about the drawbacks and limitations of dimensions. Limitations of dimensions. One of the limitations of dimensions is that dimensions do not tell us about the magnitude of a physical quantity. For example, the dimension of force is given as ml t's power minus 2. But if we write here three forces having different magnitudes, suppose F1 is force having magnitude 10 newtons, F2 is force having magnitude 70 newtons, F3 have magnitude 15 newtons. Newton is the SI unit, and in base quantities Newton is written as kilogram meter per second square. This is 70 kilogram meter per second square, and this is 15 kilogram meters per second square. We have written, I have written the unit of force in terms of base units of base quantities. As we know that kilogram is mass of unit and dimension of mass is m. This is meters, dimension of length is L, and for time dimension is T. So in each case we write the dimension as ml t's power minus 2, and here the magnitude is 10 newtons, here it is 17 newtons, and it is 15 newtons. If we write the dimension of force F1, so it is dimension of 10 into dimension of these base quantities. But as we know that numbers are not physical quantities, so numbers do not have dimension. So 10 have no dimension. So final formula for dimension of F1 is mlt minus 2. For F2 it is mlt minus 2, mlt minus 2. These numbers have no dimensions. So in dimensional formula we do not need to write that these terms. And finally we can see that dimensional of formula of force F1, force F2, and force F3. For all these three forces the dimensional formula of force is same. This dimensional formula does not contain any information about the magnitude of the force. So this is one of the drawbacks of dimensions, that dimensions do not tell us about magnitude of physical quantity. Dimensions just tell us about the qualitative nature, about the nature of a particular physical quantity. And its second drawback is that with the help of dimensions. With the help of dimensions, we can derive a formula. But we cannot find value of proportionality constant that may appear in the expression. One of the uses of dimensions is that we can derive a possible formula for physical quantity. But when we derive a physical quantity, for example, for the time period of simple pendulum, with the help of dimension, we can find time period. So its formula with the help of dimension comes T is equal to constant into square root of L over G. This constant does not have any dimension, so dimensions cannot tell about the value of this constant, and value of this constant is calculated by experiments. So experiments are needed to find the value of proportionality constant. This is one of the drawbacks of dimensions. We can derive formula, but we cannot find the exact value of constant that appears in that expression. And with the help of dimensions, we cannot derive formula in which physical quantity is equal to the sum or differences of other physical quantities. With the help of dimensions, we can derive only that kind of formulas in which a physical quantity is the uh, is proportional to multiplication of other physical quantities. For example, some unknown physical quantity depends on the multiplication of other three physical quantities. In this kind of in this kind of matter, we can derive dimensional formula with the help of dimensions. But if a physical quantity is the combination in such a way that this physical quantity is the sum or difference of other physical quantities, then we cannot derive the dimensional formula with the help, we cannot derive mathematical formula with the help of dimensions. So this is uh, the drawback of dimensions. And in next lectures we will talk about the applications of dimensions, about the uses and applications of dimensions. So we end our lecture here. For further discussions we will continue our lecture in other form.